This video explains the solution for the problem 355. As you can see, a jet strikes on a vane located on a cart. The vane has a incoming angle of 0 degrees, and then it is angled to a theta degree to horizontal. And you can see that the jet strikes on that and then slides through the vane angle and exits here. So the first thing that we should do is to mark the control volume. So that's our control volume boundary. And here we're gonna take the motion relative to the motion of fluid relative to the cart, so that you can see that the cart is moving to the right at a velocity of vc, right? It moves here. So that means the velocity of the cart with respect to Earth is vc in this direction, and velocity of the incoming flow or the jet with respect to the Earth is vj into horizontal right direction, right hand direction. And the force acts on the cart towards the horizontal direction, completely to horizontal direction, because the cart is on a platform, and then on a platform, and the cart is only allowed to move in x direction. It won't move in y direction, right? It only moves in x direction. So if you find the force force fx, so you can find the force fx to that direction. So we can apply the linear momentum equation, but we want to find the exit velocity. So we take exit velocity v2. Now this velocity is with respect to the cart. So velocity at 2 with respect to the cart is v2 in theta direction, because the jet exits the vane at a theta angle when it is with respect to the cart motion, right? If you consider the motion with respect to the Earth, this angle is not theta. It's going to be a different angle, right? You know how would you would be able to calculate the relative velocity of the jet with respect to the Earth if you use relative velocity equation. So our first task is to find the velocity of jet with respect to the cart. So I would write this equation: velocity of jet with respect to the cart is equal to velocity of jet with respect to Earth plus velocity of Earth with respect to the cart. So that means VJE minus VCE. It says CEE, I would write it uppercase letters. So VJE, again E is uppercase. VJE is VJ into this direction, and minus VCE, VC into that direction. So the resultant would be VJ minus VC into that direction. And we have V2C that with respect to the cart towards this direction. That is actually v2. So we have already that written here, so we don't need to write it again. So the first thing is to find v2. To find v2, the magnitude of v2, what we would do is apply the mass conservation. So if you apply mass conservation for steady, incompressible flow, when you have steady and incompressible, what would happen is you get this equation, integral v r dot n dA equal 0, right? So that's for the control surface. Control surface 1, I would write control surface 1, that's the inlet. At the inlet, if you look at the unit outward normal vector is in this direction. At the outlet, the unit outward normal vector is in this direction. So it's horizontal but opposite to the incoming velocity or inlet velocity. So we can write inlet velocity Vj minus Vc, that is into horizontal direction, right? That's the positive direction that we consider, Vj. But and then the outward normal vector is into this direction, so this becomes negative dA plus this is v2. V2 is positive v2 because it velocity and the outward normal vector is in the same direction. dA is equal to 0. So integral dA here is equal to aj. So negative Vj minus Vc times aj plus V2 aj is equal to 0. So aj is the common term, so we can cancel that out. We can divide the equation by aj, and V2 is equal to Vj minus Vc. Vj minus Vc. So magnitude of V2 is also equal to Vj minus Vc. Now, we have that one, and then we can write the equation in the x direction. Apply linear momentum equation. For steady flow, steady incompressible flow, steady and incompressible flow, we can write sigma f of x equal to d over dt. This steady cases, this term is going to be 0, so it's going to be vx, or x direction velocity with respect to the cart, okay? dv relative to the cart, relative velocity, plus cs rho vx relative to the cart, vr dot n dA. This term is vanished, this term goes away because of steady flow. And incompressible flow, you can take out rho from the integration in CS1, right? Vx, x directional velocity at the inlet, it is Vj minus Vc, So we have Vj minus Vc, and then we also have Vr dot n, that is negative Vj minus Vc, because the outward normal vector and the velocity vector is point opposite directions, nda, plus cs2, the second exit location. The x direction velocity is, you need to resolve the component to x direction, that is v2 cosine theta v2 cosine theta to that direction. So we take only x directional component, v2 cosine theta, it's positive direction, not in negative direction, positive direction, v2 cosine theta. And then this component, this component right here, just v2 dot n. So that's going to be v2 positive v2 and dA. And we can close the bracket, and then we have rho negative Vj minus Vc, negative Vj minus Vc, Vj minus Vc squared Aj, right? And then you have positive V2 is Vj minus Vc, so Vj minus Vc squared cosine theta, Aj, right? That's the final solution. And we can write rho can be taken out, Aj can be taken out, and then Vj minus Vc is a common factor, squared common factor. And then we have cosine theta minus 1. Cosine theta minus 1 inside the parenthesis. And that's equal to this sigma fx is only force, only x directional force is negative f of x. So negative f of x is equal to this, and then f of x is equal to rho Aj Vj minus Vc squared 1 minus cosine theta. 1 minus cosine theta. Now you can see when theta changes. When theta is equal to 0, cosine theta is equal to 0. Cosine theta is equal to 1. So in that case, this is 0. That means no force in the x direction. When cosine theta is equal to 90, so theta is equal to 90, this becomes 0, and then the fx becomes the maximum value, becomes its maximum value. So let's see B, the power delivered to the cart. So how do I find the power delivered to the cart? B is power delivered to the cart. Power P is equal to fx times V C, so that you can write rho Aj Vc times Vj minus Vc squared 1 minus cosine theta. That's the power. So what is the next question? The next question is power delivered to the cart, and also find the velocity for which C, the force Fx is maximum. Okay, what is the maximum force? When Fx is max, when Fx is maximum, theta should be equal to pi over 2. Theta should be equal to pi over 2. So if it is pi over 2, then fx maximum that means what is also find the cart velocity. Oh, okay, so we need to find the cart velocity when force is maximum. So okay, so then we need to actually find the derivative for Okay, so we need to find the derivative. We need to ask not the angle, they don't ask the angle, but the velocity. So if you can find the velocity, so it becomes maximum value. So for this to be maximum, so these are all constant. Assume that these are constants. Rho aj is a constant, and let's say theta is also constant. Then only thing that changes with the cart velocity is this. So if the cart velocity is anything higher than 0, this whole term reduces, because Vj minus Vc, if Vc is any positive value, then this value is less than Vj. So Vc is 0, then the force is maximum. So force is maximum, the Fx is max when Vc is 0. That means cart is stationary. Cart is at rest or fixed. And then the force Fx is maximum and the power P is maximum. So for power, so if Vc is 0, power is going to be 0. There's no power, right? So we need to find what the value of power. So if you find P dP, now we're going to find dP over dVc. We can write rho aj 1 minus cosine theta. Those are constants. And you find d over dVc, Vc times Vj minus Vc squared. So you can find the derivative cosine theta. We can find derivative is just Vj minus Vc squared plus 2 times Vj minus Vc, and then it's equal to, and I had to take Vj Vc out here, and then 2 times Vj minus Vc and Vj, right? And then we have rho aj 1 minus cosine theta. You can take out Vj minus Vc. That's going to be, this is Vj minus Vc plus 2 times Vj Vc. Sorry, this is going to be -1, I would say. So -1, not Vc, -1. So this is going to be minus 2 Vc, 2 times Vc, minus 2 times Vc. So we can write rho aj 1 minus cosine theta, Vj minus Vc. This is Vj minus 3 Vc. So this, when dP over dVc equals 0, P is max or min, right? So that there are two values that Vc, that two values of Vc which makes dP over dVc 0. Those values are Vc equals Vj and Vc equals Vj over 3. If Vc equals Vj, then P is 0. If Vc equals Vj, then that means this term is 0. That means P is 0. But P max occurs at this value. So when Vc equals Vj over 3, P max. So if you want to find P max is rho aj 1 minus cosine theta. Instead of Vc, we put Vj over 3 and then Vj minus Vj over 3 squared, right? And then you get rho Aj 1 minus cosine theta. Just get 2/3, that means 4 over 9, in 9, actually 9 times 3 is 27, and we get 4 Vj cube. That's the maximum power. So basically what we the concept that we used is the mass conservation as well as linear momentum in x direction, and we use the relative velocity concept to find the relative velocities relative to the moving boundary. Well, that's the end of this video. If you have any questions, let me know.